I was finally able to get my graphs to generate the line of best fit and also to display the equation of the line of best fit. But to summarize the end of the last video, when we graphed concentration versus time, we got a curve. When we graph the reciprocal of concentration versus time, we've got a different curve. But when we graph the natural logarithm of concentration versus time, we get a line. And the line has this equation right here. Okay, and so that means basically y equals 6.95 times 10 to the negative 3x minus 2.3. Okay, so there's probably a way to get that value to display more precisely. Looking over here, that's about 2.3, negative 2.3 on the graph, but I'm not sure how to get that to display more accurately. So the idea is, man, we actually know what that is very accurately, that initial concentration. It's here, it's the natural logarithm of 0.1. So let me type that in, that'll become a better value. The natural logarithm of 0.1, our initial concentration. Okay, and let's just grab the calculator and type that. The natural logarithm, where is it? Here. Natural logarithm, come on. The natural logarithm of 0.1. So negative 2.3025. In terms of significant figures, if you remember our discussion about logarithms and pH significant figures, when we took pH, that was the negative base 10 logarithm of hydrogen ion concentration. And when we did that, we got the same number of decimal places as significant figures. So we can get 4 decimal places beyond, so going out to the 10,000th place. So negative 2.3026, that would be a more accurate value to state here. And that was actually in the data right there. That's the y-intercept of our graph there. So negative 2.3026. And so I'll just update that in our 3026. Come on. For our equation. Okay, now. So here's our equation. What is it that is on the y-axis? The y-axis is, of course, the natural logarithm of concentration. So the natural logarithm of N2O5 concentration is on the y-axis. Then we've got negative K. Why negative? Because if it's a first order reaction, the integration kind of leads to this negative value showing up in here. Okay, so we've got to remember it's negative KT plus the natural logarithm of that initial concentration. Okay, so what are the values then? Oh, that was supposed to be a negative 6.95 times 10 to the negative 3. Boom. Okay, so here's our updated equation. N2O5, now that we have the line of best fit, that's the variable on the y-axis. This is negative 6.95 times 10 to the negative 3. And in terms of units, the slope the units for the rate constant here, molarity per second equals question mark times molarity. All right, that's molarity, and that's the unit we're trying to figure out. Well, K must have units of per second. Okay, so per second from the K times molarity from this gives us molarity per second. Okay, so that must be the units for K. So per second. And time, that's our other variable, that's the x-axis variable, plus the natural logarithm of our initial concentration, which has a very specific value now, negative 2.3026. So this is the equation of the line. So we can solve for the concentration of N2O5 at t equals 150 seconds. 150 seconds would fall right in here. Okay, and so somewhere between those, we'd have a concentration between here. Now it's tempting to take a number exactly in the middle of 0.05 and 0.025, but you can't do that because this data is not linear. If it were, then you could do that. You could take, well, 150 is right in the middle of that, so find the number that's right in the middle of that. But that only works for linear data. Right? If we're trying to figure out the concentration at time equals 150, it'd be somewhere in there, but it's really hard to evaluate that because this is not a line, this is a curve. But there is a way we can figure out that concentration. If we use the equation of the line, we can easily figure out what that point is. Okay, so we're going to plug in 150 seconds into our linear equation to determine what that natural logarithm of the concentration is, and then we can convert that back into concentration by undoing the logarithm. Okay, so that's sort of the plan. So we're going to plug in 150 into our linear equation. So we've got natural logarithm of N2O5 equals negative 6.95 times 10 to the negative 3 per seconds times 150 seconds minus 2.3026. Okay, so grab the calculator, and I wish that wouldn't just jump back and forth. That's driving me crazy. I wonder if I can just make this thing float. Options. Can't I just have it float, stay on top? Window. There is an option to make this thing float on top. Good grief. Well, so I've got to flip back and forth. Just minimize that. Boom. Okay. So negative 6.95 in my calculator. Good grief. that times 150, okay, minus 2.3026. Okay, so that's our value on the linear graph here, which seems reasonable, right? Something around negative 3.3. Okay, and now we just need to undo the logarithm on that. This goes a lot faster when you're not going back and forth between windows. I'm sorry about that. Negative 3.3451. How do you undo a natural logarithm? You take the base and raise e to each side of the equation. Okay? If these things in green are equal to one another, the entire expression has to be equal to the other entire expression. This undoes the logarithm, so we get N2O5 concentration. So I just need to type in that expression into the calculator over here. So my e to the negative answer, bang. Sorry, e to the answer. That's ridiculous. E raised to the negative 3.3451. Okay, and so that should be the concentration of N2O5 at T equals 150. So I've taken the linear equation and that's the molarity, 0.0353 molar. And see if that's actually reasonable. Does that correspond to the data? Is that value between what we had for 100 and 200 seconds? At 100, 0.05, at 200, 0.025, so between here, 0.0353, but it's not halfway between, but it is between, right? The natural logarithm of the concentrations were halfway between these natural logarithms, but here, that seems reasonable, okay? So at least we've got a reasonable answer, and that is how we find it. Now that we have the equation of a line, substitute in the time to find the concentration at that time.